Hello, Algebra 2. Chapter 2.2 talks about slope, and I realize this is a topic that's review and that you went through this in great detail back in Algebra 1. I've decided the best approach to this is to create a series of short videos. That way you can decide which of these videos you want to skim through. I would strongly suggest that you at least skim through each of them, and which of those then you're going to want to spend a little bit more time on. This first one here sets out, and I want to encourage you to realize that I'm going to go quickly beyond what slope is, but I at least want to set that out for you, what slope is. So you're going to remember from back in Algebra 1 that slope talked about rise over run, and that rise over run was calculated in this way. You learned to call slope m and to calculate it by looking at the change in y, in other words y2 minus y1 divided by the change in x, x2 minus x1. And that's what we're indicating here, that it's a ratio of the vertical change, the rise, to the horizontal change, the run. And I end up using shorthand for these things. Instead of calling it change in y, I often make a triangle. It's referred to typically with the Greek letter delta. Delta y means the change in y. Delta x means the change in x. And I don't want you to get confused when I do that. Now, here we get in quickly, though, to why I think this is an important topic for you to understand, because I would actually have changed the title of this section. Instead of calling it slope and rate, I would have called it slope is the rate of change. And let's talk about why. Remember that your x values are your inputs in a relation, or ultimately, hopefully, a function. That's what we'll be looking at. We talked about that in chapter 2.1. And your y values are your outputs. An example would help. Let's remember one example that we talked about in class, where we said that we wanted to look at a relation between the age of a tree and its height. So the input, what we would literally enter into a calculator or a computer, would be the age of a tree. And what we would hope to get out from that calculator or computer would be a prediction of that tree's height. So in this case, the vertical change in our information is the change in the height of that tree. Remember, that's the output. And the horizontal change on our graph would be the change in the input. It would be us one time putting in an age of 1 year and the next time putting in an age of 5 years. Likewise, though, we have talked about dependent and independent variables. Remember, independent goes with input, and both of them are on the x-axis, and dependent goes with output, and both of them are on the y. Now these words in green here, might make more sense for particular types of scenarios where maybe it's not as obvious to you as you look at the paragraph what you would put into the calculator first and what you would expect the calculator to spit back out to you. So let's talk about that example. We discussed about month and number of tourists that come to Boston. It might not feel like month of the year, like the month 6 is as obvious to you, maybe, as the thing that you would enter into the calculator. But what you're thinking about here are which one depends on the other. And we talked in our discussion last class about the idea that the number of tourists you can expect to see at Faneuil Hall depends on what month it is. So June, a lot of tourists. February, not so many. So again, we've got this change, in this case, the change in the dependent variable being associated with a rise on the y-axis, and a change in the independent variable being associated with a change on the horizontal axis. Here we'll look at another way to think about the idea that slope is rate of change. This picture ought to look familiar to you, and the first example I gave you back at the beginning of the month was this notion of number of cheeseburgers going down over time. And when I started, there were 6 in the kitchen, but then when I came back the first time, there were only 3, and the last time there were none. Well, the rate of change that's happening here visually, as you can see, is that each time it goes down by 3. So again, slope literally is that change that I see visually in the picture. oops, didn't mean to do that. And instead, I meant to do this. When you get a table, again, the slope is the change that you see in the picture, in the independent variable, as it's indicated here, as long as you're stepping forward one at a time, and I am. As I step forward one at a time in my, dependent variable, as I step forward one at a time in my independent variable, I actually climb +4 in my dependent variable. Over here, we talked about, similarly, but this time portrayed as a story, the notion that with every batch, in other words, every stage, I add another 6. That adding another 6, that's my slope. That's my rate of change. And those last two situations here with the graph and with the equation, it should be pretty straightforward at this point in Algebra 2, having taken Algebra 1, for you to figure out what the slope is. Let's talk then instead about example 6, where it presents the exact title that I was thinking of as the title for the whole chapter, Slope is the Rate of Change, or Slope is the Rate of Change. They've asked you to find the average rate of change in this story. I'm not going to read the story to you. I will assume that you do that on your own, but I do want to point out to you that in this case, in order for there to be a slope, in order for there to be a rate of change, you have to have measured two things against each other. There has to have been a relation between a collection of x values and a collection of y values. Those x values are going to be the independent variables. The y's are going to depend on the x's. Well, here are a couple of things that at least are being measured so you can see if there's change. One of those things is temperature, and the other is time. And you would presumably think that temperature changes depending on time rather than vice versa. So my green values are going to be on my x-axis. My yellow values are going to be on my y-axis. Now, how do I go about finding that slope, that rate of change? Well, like before, remember, rate of change is going to be the change in my y values over the change in my x values. It's just a matter of plugging them in, and I'll realize that the temperature went down 32 degrees over the course of 15 hours, and if you punch that into a calculator, that you'll find that the temperature dropped roughly 2 degrees per hour. The next thing the textbook asks you to figure out is, if that's the case, then what should the temperature be at 10 o'clock? And that's simply a matter of plugging in now that rate of change. I know that between 2 o'clock in the afternoon and the time they've asked about, 10 o'clock, 8 hours have gone by, and during those 8 hours the change was 2 degrees every hour going downward. So I went from 100 degrees down to 84. Now it's your turn. Go ahead and read this word problem and do the same thing. Figure out what the rate of change is. Okay, I'm going to assume that you paused, did the work, and are now waiting to see what the answer is and check your work. The change here is going to be in sales. It's the rate of sales that occurred, and that's going to be a function. That's going to be a matter of dividing the change in the number of tickets that were sold by the time that passed. 34 tickets were sold over the course of 40 minutes. So if you figured it out in tickets per minute, it was less than a ticket per minute. If you did it in tickets per hour, you multiplied that times 60 and found that 51 tickets were sold in an hour. That's it for this portion of the lesson, and you can move on to the next one, but remember your homework is actually going to be found on the website.